Confirm. Okay, thanks. So welcome. Yes. We will start yes, we can hear you. Right on time, everyone, because we have a quite packed agenda, and we would like to give as much as possible time to all the presenters to deliver their presentations. So this will be a general remark for everyone, both presenters and the participants, to try to really stick to the timing. Please be careful with the time when presenting, and if you have questions or comments, please raise them via the chat, and we'll try to address as many questions as we can during the meeting. Otherwise, we will bring that offline to the mailing list. Okay, thank you. So this is the 16th Nmrg meeting as part of the IETF 110 meeting, which will be running online this week. So welcome everyone. I am Laurent Chavalia, co-chair of Nmrg, and I think Jerome is also online, my other co-chair. Say hello, Jerome. Okay, so
hello everyone. Yes,
we have a few yes, sure, formal announcements to make. So we have a couple of slides on Noteware concerning intellectual property and participation to IETF. So this is a reminder of IETF and IETF policies in effect on various topics such as patents, code of conduct, and it is only meant to point you in the right directions. There are different RFCs and best run practices that you can look into if you want to have more information. But the main aspect is that the IETF follows the IETF intellectual property rights disclosure rules. So by participating in the IETF, you agree to follow IETF processes and policies. In particular, if you are aware of any IETF contributions covered by patents, you should declare that. The IETF expects that you file such IPR disclosure in a timely manner. For the RFC documents that the IETF publishes, IETF prefers the most liberal licensing terms possible. And so you have further references for patents and participations in the following links. Concerning privacy and code of conduct, so as a participant in or attendee to any IETF activity, you acknowledge that written, audio, video, and photographic records of meetings may be made public. And for your information, this meeting is being recorded and will be later on made available on the IETF YouTube channel. Personal information that you provide to IETF will be handled in accordance with the privacy policy that you can find at the following link. And as participants and attendee, you agree to work respectfully with other participants. And if you see any issue, you can contact us, the chairs, but also there is a team that is available if you have questions to ask. We're on the board of the IETF, so Emerging Network Management Research Group of the IETF, the Internet Research Task Force. The IETF conducts research. It is not a standards development organization. The IETF focuses on longer-term research issues related to the Internet, while the parallel organization, the IETF, focuses on shorter-term issues of engineering and standards making. So while the IETF can publish informational and experimental documents in the RFC series, its primary goal is to promote the development of research collaboration and teamwork in exploring research issues related to Internet protocols, applications, architecture, and technology. And if you want to have more information about how IETF works, you have a nice RFC that you can look at. Quick also practical information for this meeting. So the session is being recorded. There will be an automatic registration of participants once you are logging into this session. If you're not presenting or commenting, please keep your audio muted and potentially the video off. This helps also for the bandwidth management. When speaking, please state your name and any affiliation you would like to disclose. This is useful also for the minute takers. And you have a set of useful links, and I hope that if you are here connected, you already have those information readily available. If you want to, extend the experience beyond this Nmrg session, please be informed that there is also a Gather social platform that is made available by IETF for the whole IETF meeting week. And you can have some nice interactions before and after the sessions with some avatars, and it's a nice platform. You may try to test it. It's very very interesting. And sometimes also the chairs will be there online. Just finishing with that, and we switch to the next agenda item. But future meetings, we plan to have potentially some online interim meeting in April. Tentatively also in May, collocated with the IEEE IM conference. We still have to figure this out with the organizer of the conference. Another interim in June, and the next plenary meeting should potentially be with IETF 111. And we don't know yet exactly if it will be on site in San Francisco or it will be online, and the decision will be made in April 16th. So that's it for the quick news about the working group, the research group. Sorry. Quick overlook at the agenda. So we'll start with some updates, quick updates on some of the active documents of the research group. Not all the documents are here. For some of the documents, we invite you to exchange first on the mailing list. And then we have two sessions of technical talks, one on intent-based networking, and the second one on AI for network management, with a focus on some of the challenges of the AI research challenges document. So as you see, it's quite packed. So we'll start right away with Sheng, and I will present the slides for you. Yes.
Hello, can you hear me? Okay, thank you. Yeah. So, good evening, good morning, everyone. My name is Qingwu. I'm here on behalf of all the authors to present this draft digital twin network concept. So name we listed here are also this draft. We actually introduced 3 new authors, include me and Mohammed and Christian. Next. So document status. So this is not a new draft. We already presented twice. Actually, this is our 3rd time. And digital twin actually is not a new idea. It has to be widely adopted in the industry field. So one of the example like 3D printing and computing aided design actually. So here we really want to apply this digital twin concept into the network field. So the goal actually is we really want to build the digital twin platform for more efficient and intelligent management. And also we really want to leverage these to drive the innovation with more optimized service life cycle. So technical contribution from the author actually, the first is we sketch a base reference architecture based the key elements we identified in the digital twin concept. And hello, no slides now. Lauren, can you hear me? Hello?
Laurent, I don't know if you...
Actually, the slide disappear, actually.
The same issue, I cannot... Okay, let me... Maybe Laurent has a problem. Let me just maybe take your slide and share.
Bill, you want the slide 3? Sorry, I'm connected.
Yeah, slide 3. Actually, I cannot see the slides. Can you share slides to me?
We cannot see the slide anymore, Laurent. Also for me.
Okay. Yeah, we can start from this one. Actually, sorry, actually, I can hear my echo. Yeah, So for digital twin network composition, actually, we identify 5 key elements. Number one, interface. Actually, we identify 2 type of interface. One is a service interface, which will be used between the application and a digital network platform, and which can be used to get access the data and build the application and invoke the capability. The second is telemetry interface that will be defined in the interface between the digital twin platform and the physical network that can be used to populate the data and catch the data for further data processing. So number 2, data. Actually, the data actually we can connect from the underlying physical network to use to represent and understand the state and behavior of the real world twin. Number 3, models. Actually, this model based on the physical network simulation. And not only you can understand the state and behavior of the real world twin, but also you can use it to predict the behavior of the real world twins. And the data we can include such as statics data, network topology data, performance metric data, inventory data, and log data. And so number 3, mapping. Actually, we are establishing mapping between the physical network and the virtual twin network. Also, we will establish the mapping between any 2 virtual twin network if any virtual twin network can be derived from the physical network. Number 5, orchestration. Actually, this provides life cycle management of all the components. Next. So sample application scenario actually. So for digital twin network that use digital twins that use in the industry, actually we use the network as tools, but for digital twin network that are used in the network field, actually we use the network as a source, a data source. So we gave a 4 typical example. The first one, network maintenance engineer training. Actually, usually for network management, we may involve the human to do the network maintenance. Actually, for some of the tasks, actually you may really require some expertise, and to get this expertise, actually you really want to take time to learn from it, and to make sure you can reach the level that is expected. And with digital twin platform, we really can help to train this network maintenance engineer to make sure they can meet some criteria and reach the level we expect for specific expertise. So the second is machine learning training. So traditionally, when we do the machine learning training, we will get the data set, and we train this machine learning algorithm in the lab, and then we can move to the production stage. So this also not automatic, and maybe back and forth when do the lab data training has some bug. And so with digital twin platform, we really can automate this process and help to provide more efficient network management, or more efficient machine learning. So third scenario is we call the DevOps oriented certification. Usually DevOps actually will provide life cycle of software development, including planning, building, testing, deploy. And what is missing is verification. So for some of the configuration change, you need to make sure whether this configuration change can be applied actually. So DevOps actually lacks verification in this life cycle management. So so with digital twin platform, we really can leverage this platform to verify this configuration change to make sure all the validated update can be applied. And so the last one we call the network fusion. When you introduce some new network API, or we introduce some new protocol stack, before they move to the production stage, you really need to do the test and to do the bug fix. Actually, we can leverage the digital platform to automate this process and can provide a more efficient this network bug fixing. Next. So when we look at this job, actually, we discuss this. We think this is a very useful work actually, but we identify several issues. We need to reach agreement between the author. Also, we want to solicit the feedback from the Nmrg community. So first is issue one. How data is different from the model. Actually, as we know, that in the digital twin network composition, we actually identify 5 key elements. So in industry digital twin entities, actually data and model are actually apparently 2 common and separate components. For example, in the smart manufacturers, in the smart factory, actually we can define the data and model separately. And of course, actually, data and model actually they need to be used together. Actually, data can be structured to follow a set of well-known data model requirements. And so in the digital twin network, we propose in this draft and data model, we think also the first let's take a look at their definition. For data, actually, it is digital twin data. Actually, they can use to represent to understand the state and the behavior of the real world twin. And for model, actually, we identify 2 kind of model. The first is computation and analytics model. That can be described, not only describe, understand the twin operation state and behavior, but also can predict the twin's operation state. The second model we identify is used to prescribe the action based on service logic. One of the typical example is a policy-related model or like a event condition action model. Actually, they can provide prescribe this kind of action. And so based on this definition analysis, we think actually data and model should be separate. And data is a cornerstone for construct a digital twin system. For model, actually, this can be seen as a source to analyze and diagnose, immune, and control the physical network. Next. So for second issue is in the 5 key elements, the orchestration is one of important key elements. Actually, basically, orchestration component actually used to control and management twin entities. And with application-facing interface, it can help to provide integrated service to various applications. So we try to figure out how this orchestration is different from the other key elements. For example, model. Actually, one model role is to prescribe that action based on service logic. So now we can see actually for orchestration, they also can be broken down into 2 roles. The first role is they can control digital twin network environment and its components to derive required behavior. The second is it's a main role for the orchestration component. Actually, they will provide life cycle management for all these components. And it can provide repeatability and it can provide reproductivity. And based on the definition we gave here. And so seems there's some overlapping with the model role we mentioned in the previous slides. We need to figure out how to address this kind of overlapping.
Sorry to interrupt. We need to ask you to finish in 2 minutes the presentation to keep with the schedule. Sorry.
Oh, okay. So let me try to be quick. Actually, move to the next one. So we also have 3 other issues, and we already discussed with the author, and we actually like to solicit feedback for. One of is how should the interface should be defined. We identify open standard interface and internal interface. So our conclusion is we can start from this open and standard interface, and later on we can revisit this internal interface. Next. So the next issue is for one of the key element actually who responds for the checking difference. Actually, we think it's in mapping, and then we support two kind of mapping. One is one-to-one mapping. The second is one-to-many mapping. The key difference they actually for one-to-one mapping is between physical network and digital twin. They require continuous flow data exchange. Actually, it is a huge amount of data exchange. But for one-to-many mapping, actually, they just occasional data exchange between the two digital twin network. Yeah, next. So last one is continuous verification is we propose in this draft. How this is different from CI/CD? Actually, as we know, DevOps, provide the whole life cycle management, include CI/CD, and we give the example. Now, based on our evaluation, we think CV is extension of DevOps or CI/CD. One of the example we give actually, relate to the DevOps-oriented certification. Actually, because it lacks the continuous verification, it will end up increase the risk to deploy no validate update. But with continuous verification, we can address this issue. So we will reflect the summer change in the next version. So next step, actually, we will keep on investigate related digital twin worker not only in the IETF but also in other SDO and identify their difference and commonality. Try to make it solid in the introduction and abstract. And also we will further articulate the relationship between the data model mapping. And also we will analyze the requirements from the twin and application interface. And so we like to hear your feedback, and we will address any issue raised in the meeting. Thank you for listening. Get back to you, Lauren, Jerry.
Unfortunately, we have no time for questions and comments now, so that will be have to be taken offline in the mailing list or after in the gather-thon. We can also discuss.
Okay, we're gonna take it to this. Yeah.
So sorry, we have to keep time. Sorry.
Okay.
Next speaker, I think, is Olga.
Thanks, Lauren. My name is Olga Havel, and I'm from Huawei, and I will be presenting the draft for intent classification today. Next. So I just want to refresh on why, because last time there were a lot of questions around it. So I just wanted to repeat very high level what were the goals overall for the Nmrg and what was proposed. So the Nmrg goals were to agree on intent-related terminology and classification and provide a foundation for future discussions related to the intent and where all participants have the common understanding. So it is really about the sharing of terminology and the concepts. So originally the two Nmrg drafts were proposed to address this goal. The first one is not the one we are talking about here. It's the concept definitions to clarify the concept of intent, and they also provided the overview of the functionality. And this draft today that I'm presenting is the classification draft to provide intent classification and develop a taxonomy for the intent-based networking or intent-driven networking. Next. So the scope of this draft, there was no clarity originally about what intent represents for different stakeholders. So we had a concept draft that gave some high-level concept definition of the intent, and it also presented the overview of intent functionality, intent networking functionality. But that's not enough. We needed really to give more information and to do some classifications of different intent types in order to understand what intent represents to different stakeholders. And those stakeholders could be network operators, administrators, end users, customers, etc. There was also no common understanding how to classify intents and what types of intents exist. There were different types of intents being used in different scenarios, and there was no kind of common taxonomy there. So this draft addresses these issues by proposing intent taxonomy and methodology. Next. So as you know, we proposed a methodology that could be used to deliver to generate this intent taxonomy and also to extend it and customize it. So we explained this many times previously, and there were a lot of comments suggesting to add an example, and therefore we added an example, which was the IETF 108 POC, a multi-layer approach for IBM. Barbara Walter and the others, and it's been used as an example for kind of how the classification methodology could be used. So for those who are familiar with this POC, they have two types of intents. They have a slice intent and they have service chain intent. And after discussion with them, we determined, yes, that their POC could be used for carrier, but also for data center. So then we identified what type of solutions or scenarios, what type of intent user types, what type of intent types, what's the scope of the intent, what's the network scope for the intents, how they're abstracted, are they technical, non-technical, are they persistent, are they not transient. So we used this methodology and taxonomy, and there was no need even to extend it because we were able to fit and classify their use case according to the taxonomy. So you can see here for carrier, we used kind of different symbols, different colors for carrier and data center, and where these intents fit into the overall taxonomy and classification. Next. So we really want to acknowledge everyone who reviewed, suggested, commented, proposed text for this draft. There were many people who helped and who gave their input. Mehdi, Brian, Laurent, Alexander, Yehia, Jeremy, Pedro, Daniel, Branislav, Bob, Jürgen, Charlene, Jeff. We also thank Barbara, Walter, Molka, David for their contribution and for providing the multi-level approach POC, which we used as a use case for intent classification, as a sample for the use case intent classification. Since we shared the version of this draft, version 2, we also got review comments from Molka, David, and Benoit. Thank you all. Sorry, this was written before Benoit contributed, so I will add him to the acknowledgements. Next. So the following are the issues that we resolved in this draft. So we sharpened our draft's position. There were 38 comments in total, but this is just kind of, we grouped them into 8 high-level categories just to explain what we did in the version 02. So we sharpened our draft's position in relation to the concepts draft. Then we provided detailed description of the intent classification workflow and how we can use the methodology to extend the taxonomy classification. Then we integrated, as I mentioned, the POC into the draft and use it as an example for our classification. There was some requirement to clarify further requirements for different intent types based on the context. We added that. We addressed the benefits of intents to different network requirements. We added the scope section, so we moved some text there and we kind of identified the scope and priorities for the project, and included definition section, introducing different terms related to IBN, IDN with reference to IBN concepts and overview. And then we had, there were various readability improvements. But we did receive some further comments that we would address in next few days. Next. So then we asked for the RG last call, and then Shepard has been assigned since the last IETF meeting. Laurent has been assigned as Shepard, and the 3-week RG last call was initiated on 23rd of February. So we are now collecting the comments, and I already mentioned that we received some comments, and we'll be receiving them until 15th of March. Next. So this is just the document timeline for those of you who are not maybe familiar, but you can see that we have many versions of the documents, many revisions, a lot of the comments. The draft has been revised many times. We addressed all of the comments from the community. We believe this the document is very stable and it's ready for ISSG review. We spent a lot of time on this document and we really think it is ready now. So you can see the timeline for RG. So next steps, we believe that the authors, co-authors believe all reported issues are resolved at this stage. We will continue collecting comments from the group from the research group by 15th of March. We will make one final revision of this document that would address these comments, and then there would be shepherd evaluation and hopefully finally ISSG review. So these are the next steps. Thank you. If you have any comments, I don't know if there's any time learned.
Can you hear me?
Yeah, I can't hear you, Lauren.
Hello, hello. Okay, sorry. Yeah.
Yes.
It's better
Now
for
we
the
can
sake
hear you
of
now.
time that we take those comments offline on the mailing list. I saw that Benoit was going into the queue, but just for the sake of the other presentation, and this is anyway a research group document that is under research group last call, so please handle those comments offline, please.
Thank you very much. Thanks. Bye.
So. And Jan, you will be the next speaker, please.
Okay, this is Dan Yangchen from China Mobile, and this time topic is about the updates of the network measurement intent. And next slide, please. Hello? Hello? Okay, and the updates the main updates includes 2 points. One is the update of the overview of network measurement intent process. And the other one is taking network measurement intent in SLA as a concrete example. And next slide, please. So for simplicity, we will use NMI instead of network measurement intent. And the major components concludes the file part, the file parts, and the sequential relationship between the components is shown as a red figure. And next slide, please. And the functions of each component are as follows. In NMI recognition and acquisition, NMI will be recognized by ingesting users or network operators' measurement intent. They have the ability to identify the NMI of a certain network performance that users want to measure, such as delay, jitter, and so on. At the same time, allow users to express the NMI of network performance in a variety of interactive ways to ensure the accuracy of the identification of the NMI. And in NMI translation, NMI needs to be translated into actions and requests taken against the network. So determine the content to be measured. And according to the previous NMI translation step, the NMI orchestration and pre-verification determines the measurement scheme according to the required measurement content and equipment support degree, and pre-verifies whether the measurement scheme is feasible. And next slide, please. So in NMI, data collection and analysis should be based on the selected measurement scheme, and the content to be measured that's determined in the previous steps automatically realize the collection on demand and generate corresponding data analysis results. So at the end, NMI compliance assessment verifies whether the results meet the requirements and whether the NMI is satisfied. So if either of the two conditions is not satisfied, the NMI should be modified and re-enter the NMI orchestration and pre-verifications. And if it meets the requirements, it will put out the measurement results. Next slide, please. And we will give concrete examples. At present, a variety of network measurement techniques have been developed, such as the active measurement and the passive measurement. But no matter which measurement technology will occupy the network resources. For example, if the transmission frequency of active measurement message is too fast, it will occupy too much bandwidth resources and affect the normal operation of actual business. Well, if the transmission frequency is too slow, some instantaneous network anomalies will be missed and the network status cannot be accurately reflected. So in order to accurately measure the network stage, and especially the abnormal network affecting the business, while occupying the network bandwidth as little as possible, and taking into account the low processing capacity of the data analysis system. We take the delay measurement scheme in SLA as a service level agreement performance measurement as an example to illustrate. First of all, we will set different thresholds as a warning value and alert value for network delay in advance. The network delay between different thresholds represents the different status of the network and the business. When the delay value is below warning, the network and the business are both normal. And when the delay is between warning and alert, it represents that the network is normal, but the business is it represents the network fluctuation is abnormal, but the business is normal. And when the delay exceeds the alert value, both the network and the business are abnormal. So we should adopt different measurement schemes in different when the network delay in different values. So next slide, please. So when the network delay exceeds the alert value, or when the historical data predict that the delay will exceed the alert value, when we adopt passive measurement, it requires 100% sampling of business data, and the transmission frequency of active measurement is modeled to the maximum. At the same time, the log of alarm and the alarm data of the whole network equipment are collected to realize the most fine-grained measurement of the network, and then to locate the root cause of the problem and repair the network in time. But when the network delay exceeds warning value but is lower than the alert value, passive measurement samples 60% of business data, and the transmission message frequency of the active measurement is adjusted to the median value, and the running state date of some key devices in the network is collected. And when the network delay is less than warning value, passive measurement data is sampled at 20%, and the active measurement message frequency is adjusted to the lowest, and the network equipment running stage of key nodes can be collected as needed. So these steps are all predefined, and we will adopt different strategies in different situations. And next slide, please. So after defining the measurement strategies at different thresholds, the following steps are performed for each network measurement intent component. First,
sorry to interrupt. We have to ask you also to finish in 1 minute now.
Okay.
Thank you.
And this is the SLA performance with measurement with the NMI concrete stamps, and it's and the next slide, please. So next steps, we will discover more concrete examples of the network measurement intent, and we want to incorporate this case into the IBN use case. And looking forward to your components, suggestions,
Thank you.
or any questions.
So as for the other presentation on the research group documents, we will ask you to handle any comments or questions on the mailing list or with the authors, please. So we will switch now to the technical talks on intent-based networking. And our first speaker will be Kazuki Tanabe from NEC. Yes, we can hear you.
Hello,
Let me
can
just
you hear
check the slides quickly. Okay. Okay,
Yes,
you can go on.
this is mine. Okay. Hello, everyone. I'm Kazuki Tanabe from NEC Corporation. Thank you, Laurent and Jerome, for inviting me to the Nmrg meeting. I'm very glad to present our work here. Today, I'll talk about our work published in CNSM 2020 titled Automated Performance Evaluation of Intent-Based Virtual Network Systems. Next, please. Next, please. First, I'll explain the background and purpose of this study. Next, please. Recently, the growth in virtualization technologies enables easy and rapid deployment of various scales of infrastructures. And then, automation technologies are highly demanded in the field of ICT system integration to speed up each process and reduce engineers' burden. There have been several studies, including our work, targeted at requirement definition to deployment phases, but the number of studies for testing evaluation phase is limited, especially for networking level evaluation. Meanwhile, as all of you may know, intent-based networking (IBN) is a concept proposed by Cisco in which the network system is managed based on users' abstract intents. In this study, we target the automation of testing phase by following the concept of IBN. Next, please. Before introducing today's topic, let me introduce ongoing project of our research group. In NEC, we have proposed and developed Weaver, which is an AI-empowered network system designer. Weaver accepts an abstract intent as an input and recursively refines the abstract part of the intent and generates huge number of system design candidates. Weaver accepts an abstract intent. Then, Graph AI, trained by reinforcement learning, evaluates each candidate and chooses the most appropriate candidates as an output system topology and configuration. For more details of Weaver, please refer to the following paper in Proceedings of IEEE GlobeCom 2019. Today's topic, our automation technologies for performance evaluation, is partially related to our Weaver architecture. Next, please. Okay, let's go back to today's topic. As I explained now, Weaver defines concrete system design from abstract requirements for design phase and deployment phase in system integration for IBM-based systems. Since system requirements are composed of abstract users' intents, there are multiple methods to realize the required functions, such as virtual or physical infrastructure, native or middleware-based applications. So, multiple candidates of system design can be generated. Next, please. After these system designs are deployed, the satisfaction of system requirements is determined in testing phase. In this phase, engineers generally develop evaluation programs to evaluate the functionality and performance of the deployed network. This evaluation program depends on each system design because available packages and commands are different for each OS, and the syntax parameters of scripts differs according to the network configuration. So, an evaluation program developed for a system design cannot be applied to another system design, which puts a heavy burden for engineers. Next, please. Therefore, our goal is to automate such network-level testing phase of SI, especially for IBM-based systems. Today, we propose an automated generation method of evaluation program. Our method accepts a set of system requirements and system design derived from requirements and generates a program compatible for the system design despite the difference of OS or network configuration. By introducing our method, engineers' burden will be drastically reduced and IBM-based SI will be dramatically accelerated. Next, please. Okay. Second, I'll explain the detail of our proposed method. Next, please. First, let us explain the model settings. In this study, we model both a system design and system requirements as directed graphs composed of the set of nodes and edges. A system design is a concrete network configuration and system requirements are abstract expression of the system design. Evaluation units, which are related to users' intents, are expressed as abstract nodes or edges. System components such as virtual machine, OS, and applications are expressed as nodes, while the relationship between nodes are expressed as directed edges. Several nodes have some configuration parameters as their own properties, and each node and edge has its own type. Next, please. This is the outline of the proposed method. Our method accepts a set of system requirements and the system design. To generate a correct evaluation program, parameter search on the system design graph runs for each evaluation unit by referring to evaluation templates. Evaluation templates define abstract commands and search methods for parameters of these commands. Acquiring parameters, abstract commands are translated into executable evaluation scripts by referring to command templates and substituting those parameters into the script defined on the template. Next, please. Next, we'll explain the detail of parameter search step. In this step, the method refers to the evaluation template corresponding to the evaluation unit. An evaluation template defines an abstract command and search method of its syntax parameters for each evaluation unit. For example, evaluation unit bandwidth up to up means a minimum requirement of communication bandwidth between two applications. This evaluation template of this evaluation unit contains a command which contains 5 parameters like agents, OS types, and destination IP address, and one constraint for bandwidth. After the command is obtained, the parameter searches in the system design graph are conducted by following search method for each parameter, and acquired parameters are substituted to the syntax. Next, please. Okay, after the parameter search step finished, the abstract commands with parameters are translated into the concrete evaluation scripts by referring to command templates. Each command template defines mappings from an abstract command to ordered tuples of executable scripts and their agents. Each tuple of a script and an agent has conditional branches based on the input parameters. For example, if the type of client OS is Ubuntu, these red scripts are chosen and acquired parameters are substituted to the syntax. Finally, evaluation program is generated as a list of evaluation scripts for all evaluation units. Each script is sequentially executed by the agent, and some evaluation scripts for performance measurement compare the results from predefined constraints. Next, please. According to these two steps, an evaluation program is automatically generated by our method. Next, please. Third, I'll explain the detail and results of evaluation experiment using our method. Next, please. To show the effect of our method, we conducted experiments to verify evaluation programs generated by proposed method. In our prototype implementation of the method, evaluation programs are generated as workflow of evaluation scripts, which can be executed by Ansible. We deploy the system design on an OpenStack virtual environment. Next, please. First, the left-hand side of this figure is the system requirements for connection between applications. In this example, an HTTP connection from app 1 to app 2 and minimum bandwidth of 500 Mbps are required. And the right-hand side is the system design derived from the requirements. In this system, both the client application app 1 and the server application app 2 run on different Ubuntu OS nodes, and Nginx is used as an example of app 2. Each Ubuntu node is hosted on different VM node and provisioned by different Ansible instance. These two VMs belong to the same virtual subnet VL, and vRouter node connects between VL and the internet. In this setting, we generated and executed evaluation scripts for two evaluation units, HTTP app to app and bandwidth app to app, by using curl and hyper packages. Next, please. Here's the execution results of the environment 1. As you can see in the table, both the evaluation scripts have the correct program output and are determined as pass. Like this, the satisfaction of system requirements can be automatically determined by evaluation program generated by our method. Next, please. Second, we added two VMs to the evaluation environment 1 and created some background traffic by SCP file transfers from these new VMs to Ubuntu 2 node. We executed the same evaluation program in this environment. Next, please. Here's the evaluation results. As you can see in the table, the results for bandwidth up to up turned to fail due to the shortage of bandwidth performance. This throughput reduction is because of the background traffic generated by additional VMs and performance reduction of Ubuntu 2 node by processing file transfers. These results show that the evaluation results can be determined per evaluation unit related to user's intent. Furthermore, the results help easy detection for system components which need improvement even though the performance is not enough. Next, please. Finally, I conclude this talk. Next, please. Okay. In this study, we propose a graph search-based automation method to generate evaluation program in IBM-based system integration. We modeled system requirements and designs as graph structures, and the parameter search algorithms run in a system design graph to acquire parameters of scripts. For future works, we are planning to expand our parameter search algorithm so that parameter can be acquired in much more complex topology. Next, please. That's all. Thank you for listening.
Hello, can you hear me? Yes, we have time for one. I was saying thank you, Kazuki, for the presentation. I think we have time for one question. Sorry, I have some issue with the Meet setup here. Apology for that. Okay, if there are no questions from the room, Katsuki, thank you for presenting your work from CNSM to the Nmrg. We will surely come back to you. I mean, I have, in fact, more than one question, so I will come back to you offline, because I think some of the aspect that you are using as techniques could be very useful in the context of internet-based networking, and I would like to hear more from you. So I will follow up by email. Thank you. Okay, so we switch to our second talk in the internet-based networking topic, which will be with Shiyam on SDN heading north. Yes, we can hear you. The floor is yours.
Hello, everyone. Can you hear me? Okay, this is Shiam Al-Anmari. I'm a PhD candidate at Lancaster University, and in this research, I would like to discuss how intents can be used as a communication mechanism between service consumers and service providers. Next, please. So SDN is a networking paradigm that overcomes the limitations of traditional networks, but the success of SDN mainly depends on the ability of SDN users and developers to leverage these capabilities. They usually use the northbound interface, or NBI for short, to communicate with the network. Therefore, the NBI is key enabler for the realization of the ultimate SDN promise. Now, in our research, we have decided to focus on intent-based MBIs because they're gaining a lot of attention today, both in industry and academia. Next, please. So here's the outline of my talk today. First, I will discuss the main challenges with the existing intent-based solutions and the limitations with the related work, and then I will propose our intent-based framework and expressions. Later, I will discuss our preliminary results in the context of a cloud CDN use case and intent refinement. Finally, I will conclude and discuss our future work. Next, please. Before I start, I think it's important just to differentiate between intents and policies as we see it. So policies are prescriptive rules that determine what kind of actions to take under different circumstances. They're usually articulated by system experts like network admins, whereas intents are declarative expressions that allow users to express the desired outcome at a higher level. So they can also be used by non-technical users as well. Next, please. Since the development of intent-based MBIs today remains in its infancy, there are several challenges. So the first challenge is that most of the existing intent-based solutions are designed for network experts, and therefore they provide prescriptive intent expressions rather than declarative ones. And in our research, we wanted to focus on generic service consumers who do not necessarily acquire technical knowledge. Therefore, they need generic declarative expressions rather than the existing prescriptive ones. The second challenge is the translation process between the declarative intent expressions and a form that is understood by the underlying system. But we think it's important to have an intermediate level of translation where we break down or decompose these declarative intents into a set of abstract policies that are technology agnostic. And the reason to do so is to provide, of course, more flexibility and reusability. The third challenge is that we need to have intent solutions that are platform independent and not tightly coupled to specific SDN controllers. And they need to also be extensible, which allows creating new intents. Next, please. So here are some of the limitations with the existing related work. So most of the existing intent solutions are limited. They're ad hoc. Some of them are vendor specific. And since most of these works mainly focus on the networking and NFV domains, so the intent expressions that they provide are considered to be prescriptive. So in our case, we need to have generic and declarative intent expressions that are beyond the network domain. Moreover, most of the current works do not really provide the means or the tools to create new intents and map them to lower level policies. Next, please. So to address the aforementioned gap, we have proposed an intent-based MBI framework and expressions. So our framework consists of 3 layers. The first layer is the northbound interface, which connects the service consumer and service provider via their corresponding APIs, and it's responsible of mapping these intents to their equivalent policies. The second layer is the intent and policy management layer, which is responsible of calculating and updating the technical requirements and operational parameters of these policies. So it continuously monitors the system and monitors how far it is from achieving the intent target and updates these requirements accordingly. The third layer is the service management layer, which consists of microservices that are managed by the service orchestrator, which will translate these policies into microservice API calls. Next, please. So I'll discuss our proposed generic declarative intent expression. It's expressed in terms of service, resources, conjunction for readability, and target. So this can be decomposed by the intent developer or the service provider into a set of prescriptive policies that are connected using logical operators like and or, and each policy could be expressed in terms of conditions, actions, constraints, and optionally priority. Of course, we need to maintain the mapping between these intents and their corresponding policies, as you can see in the table below. Next, please. So for demonstration purposes, I will discuss our preliminary results in the context of a cloud CDN or a content delivery network use case. So in this situation, the service consumer would be the content provider who wants to cache their content in a CDN, and the service provider would be the CDN operator who's managing the CDN. So today, cloud CDNs do not really allow content providers to express their high-level intents. So in our solution, we would like to have content providers expressing their intent. So they can say something like, hey, I want caching for content X to handle 20 gigabytes per minute. So in this case, the target in this intent is to hit this specific workload. This has to be decomposed by the CDN operator into a set of prescriptive policies. However, we also need to keep in mind that these intent targets could be underestimated, overestimated, or well estimated and take the corresponding actions. Next, please. So in this figure here, we have shown how the workload has been achieved throughout the day by varying the cache's cluster size, which means adding or removing caches according to the demand. So the baseline is a traditional cloud CDN behavior that reactively scales the cluster. And we have compared this against our intent solution in two cases. The first case is an underestimated intent workload, and the other one is a well-estimated intent. So in both intent cases, we have achieved better workload than the baseline, but of course, with a well-estimated intent, we can get even better results with the workload. Next, please. So one of the most important features of intents is their ability to honor the intent target even under changing circumstances. So intent refinement is key. And by refinement here, we mean the process of continuously updating the technical requirements or operational parameters of these intents to meet like the requested target. So in this case, our goal was to maximize the workload. So one way to do so is by proactively scaling the cluster. So there are two approaches to take, either a conservative or optimistic approach, or a greedy or pessimistic approach. Next, please. Yes. So in this figure, we have compared the cache's cluster resizing behavior in these three scenarios. So in a no intent scenario, which is the baseline that does reactive scaling of the cluster, and then we have compared this against our refined intents, both greedy and conservative. Of course, this comes at additional cost of a running uptime. So this has to be tuned by the CDN operator. Next, please. So in this figure, we have compared the workload in these three scenarios. With the refined intents, we were able to achieve more workload. Of course, the greedy approach was the best, and then the conservative one, and the last, of course, was the baseline, which is a no intent scenario. Next, please. So to conclude, we have discussed the limitations of the current intent-based solutions, and therefore we have proposed an intent-based MBI framework, along with some declarative intent expressions and their corresponding prescriptive policies. We have also demonstrated a caching intent with a workload target and its corresponding policies. We've also discussed some possible intent refinements in cloud CDN use case. Next, please. So as part of our future work, we plan to extend the current static mapping between intents and policies to have a dynamic one based on several criteria and map them to existing microservices. We would like to also investigate different intent targets other than workload, like probably latency. And finally, we want to implement this in a real cloud-based testbed, along with the required APIs and translations. Thank you very much for your attention, and I would like to have your questions if we have time for that.
Yes, thank you for the presentation. We have time for one or two questions, I think.
I do have a question, but I'd like to hear from the floor first. I do have a question, but I'd like to hear from the floor first.
Yes.
Okay, so my question is on the evaluation, the two slides that show on the evaluation, especially on this one. Just can you give us a kind of, let's say, a way of differences between the different approaches, because it's really difficult to read.
I can't hear you.
Yeah. Laurent, the sound was not really good. Maybe if you can just put in chat.
Oh, yeah, I'm back. Sorry for that.
The question.
Just like to have, if you can explain or give us some figures about the code that you have with your different approach.
Oh.
Laurent, we did not hear you very well, so maybe just put in chat if you can.
Yeah.
Okay, I think he has some issue with his audio, so I think we. Okay, yes. So maybe he will send you the question offline directly, because I think he has some issue.
Yeah.
So thank you again, and so we will now move to the next speaker. There is no other question. There is one question, maybe. I'm not sure.
Hi. Hi, it's Phil here. It was a nice talk, thank you. I was just wondering, in terms of your example with the cloud CDN, how did you talked about the intent there? Was that something you talked with those sorts of providers about what kind of intent they would like, or this is just sort of an example, a working example that you kind of decided what you think looks sensible things to pick?
Yeah. So no, we haven't talked to anyone really, but we have looked at the existing cloud CDNs, the popular ones like Google Cloud, like AWS, etc. And we have noticed that they don't really provide content providers with this kind of flexibility. So this was one of the examples that we thought about. Actually, it was inspired by one of the works that we have read about, which was talking about futuristic CDNs, where they would like to allow content providers to express higher level requirements, but that was not really formulated or encapsulated in the form of intents, and therefore we decided to actually build up on that idea and adopt the intents solution in this context.
Thank you.
Thank you.
Okay, so thank you again. And we will now continue with the next presentation. So I think it's Joe. I don't know if Laurent can share the screen. I think he has some issue. So let me open the presentation, maybe.
No, hello, can you hear me?
Yes, Laurent, we can hear you.
Okay, so Joe will share the screen itself because he has a video demo embedded, so we agreed that he will share. So Joe, if you can ask for sharing screen, we will grant you the access.
Okay, sorry, just Bear with me, you can hear me okay?
Yeah.
Yep.
Okay. Is this full screen on your side?
No,
I'm
we
not
can
too
see
sure.
if you go maybe to the slideshow settings, you may be able to switch the last row in the, maybe you can change the,
Ah, okay.
okay, it's good.
Okay, so hello everybody. My name is Joseph McNamara. I am a PhD student studying under an Irish Research Council funded enterprise partnership scheme with Athlone Institute of Technology and Ericsson. I will be presenting my recent work in the area of intent in an adaptive policy environment, along with a demonstration of intent in action. The presentation will be broken down in the following way. First, we will cover the paper contribution. Next, I will describe the architecture of the system, along with the usage scenario to be demoed later in the presentation. Next, we will describe the 3 primary steps in how the system handles intent. This is performed in order of intent generation, intent comparison, and intent resolution. I will then present a video demonstration of the system in action, where we use intent to configure Mininet emulated networks with parameters described through intent. And finally, we will discuss what we have learned from our work and how it has directed our current focus and approach. So this work presents a 3-step mechanism for intent realization in an adaptive policy environment. Intent has been a topic of discussion for a very long time, even longer if you associate it with the goal-based policies from the late 1990s. In our work, we looked at intent as a way to reduce network complexity, and of course, this is not a new goal and has been actively pursued by the research community. But we wanted to investigate, what does a system need to be intent-driven and adaptive? Our result was a 3-step mechanism that I will describe and demonstrate in this presentation. In the system architecture, we have intent messages on the left side of the diagram. We have an adaptive policy execution engine Apex shown as the yellow box, and a network underneath to represent our Mininet network emulation tool. An intent message will arrive from the left side of the diagram. This is received by the policy engine, triggering a validation cycle. This process checks the message that it can be processed, and then starts comparing the new intent to already existing intents stored within policy context. If no conflicts are detected, the intent is added to a collection. If a conflict is detected, the intent is rejected and the issuer is notified. The addition of a new intent to the collection triggers a reconfiguration of the network, where the intent collection defines the scope for acceptable network parameters. In the next slide, we will provide more details of this process. In this slide, we see an example of an intent passed into the policy engine. Characteristics of the intent message are a recursive structure, which allows for intents of varying levels of detail while maintaining the system's ability to fully navigate each message. A range of optional keywords, who, what, when, where, how, maintains the readability of the message for both the user and the policy engine, while complementing the varying levels of detail achievable within each message. In this example, who describes the user, what is a generic label for the intent, when describes a time frame for the intent to be active, where describes a condition for the intent, setting bandwidth to less than 1 megabyte per second, and how, which is included for the example but is set to null as it does not play a role in the usage scenario. The intent message is received by the policy engine, where it is parsed into an internal path collection. In this slide, we detail the intent comparison step. The intent message has been processed by the policy engine into an internal path collection. Each path through the tree can be easily compared to branches of different intents. Using this approach, relationships are easier to identify on a structural level. Intents with similar structures are often related. However, format alone is not enough to compare intents. To properly compare attributes, we must be able to identify and understand what it is we are comparing. To compare attributes, we must first know what they are and how they behave. This resulted in the incorporation of a dictionary with the policy system. The dictionary enables the identification and predefined elements. The dictionary enables the identification of predefined elements such as bandwidth, and provides a predefined blueprint for the intent element to be mapped to. Mapping intent elements provides functionality, adjusting our action to generate responses that are aligned with all current active intents in the system. In this case, as more intents are introduced to the system, the goals of the network change to fit the shifting of acceptable thresholds. The graph shows output similar to the demonstration you're about to see. In this scenario, we implement 3 straightforward intent messages. The first intent message requests a bandwidth of 1 megabyte per second. This is more than necessary for the video we are streaming over the Mininet network to generate traffic. The second intent message requests a bandwidth of about 375 kilobytes per second. As this intent does not conflict with the already existing intents of the system, it has been validated and has triggered a reconfiguration of the network. The third intent message requests a bandwidth of about 190 kilobytes per second, which is compared to the 2 already existing intents and triggers a third reconfiguration of the network. So this means I have to move. Apologies, I didn't have this ready before the presentation. Okay, so the demo starts with the running of the Kafka cluster, and next we run Apex inside our Docker container. Then we build the policy and deploy it onto our Apex engine. Now our policy is running and is listening for our Kafka topics. Now we run our application, which sends an intent message to the system and receives back a response and builds the network according to the specified parameters. A video stream is started to generate some traffic on the network, which we will step through later. I can skip ahead now just to save time. So after streaming for a few seconds, we're going to introduce a new intent into the system, reducing the bandwidth of the configured network. The new intent triggers a reconfiguration and starts another video stream. And after a few more seconds, we introduce the third intent message into the system. So now I can move ahead and look at what's happening in policy. So the intent is received and
Hello, Joe? I cannot hear you anymore.
Joe, we can't hear you. I think you still think you're doing it.
Yeah, I think the issue is that he's not hearing us too, so difficult to trigger him. Let me see. Trying to contact him. So maybe let's see. I will revoke the screen sharing for a moment just to trigger him. Not sure there is any other option. Joe, can you hear us? Joe? Joe, I hope you can hear us. We have lost audio on your side. Hello, Joe. Can you try to reconnect audio or do something maybe on the chat? Okay, so apologies for that. Just for the sake of the meeting, we will switch to the next presentation, and hopefully if Joe reconnects, we will just try to give him a couple of minutes to conclude his presentation. But let's switch to the next presentation in the meantime. Stefan?
Yes, hello, can you hear me?
Yep.
Yes. Great.
Let me just share my screen. You can go on.
It's not full screen, but no, okay, great. So yeah, hello, thanks again for inviting me. I'm Stefan Schneider from Paderborn University, and I'd like to present our work on self-driving network and service coordination using deep reinforcement learning. So as the previous talks, this is also based on our paper at CNSM last year, and I'll try to give a reduced version of our conference talk and in the end focus on challenges of applying AI for network management. Yeah, so let's get started. Next slide, please. So in NFV, or when we talk about microservices in a service mesh, or even machine learning functions in a pipeline, we often have services that consist of multiple interconnected components. And here I just call them C1, C2, or could be C3, C4, and so on. In addition to these services, we have our network that's depicted here by the clouds, which consists of distributed but interconnected nodes, where each node may have some kind of compute resource, limited compute resource. And then we have our users that want to use these services. And in order to provide these services to our users, we need to scale the service components, place instances of these components at the different nodes, and then schedule the rapidly incoming flows from these users to these different instances. Next. So for example, here I placed an instance of component C1 directly at the ingress node, and then an instance of C2 at the neighboring node, and steered the traffic through those nodes. If I see, for example, exactly if that the load at the ingress node is becoming too high, then I can scale out this component C1, sorry, and place a second instance of C1 at the neighboring node, and then schedule some part of the traffic to the second instance to push the load away from the ingress node to the neighboring node. And of course, in this scenario, nothing is static. Everything keeps changing all the time. Users arrive, traffic goes up, goes down, traffic arrives at new locations. And so we have to rapidly react to these changes and adjust our scaling, placement, and scheduling here. Next, please. So this whole scenario isn't new, so there's a lot of existing work actually. But when we looked at existing work, we found that there are often three major limitations of applying this existing work to practice. And the first is that often existing work focuses on mid to long-term planning per deployment request, assuming that they have some expected load of, or some expected load, and then they run some algorithms, place instances, hardwire them to the ingress nodes, and you hope that it works. But the problem is that operational reality often diverges from such initial plans if the load is different, for example. And so we really focused on the rapidly incoming user flows here and on scheduling these flows at real time and adjusting our scaling placement dynamically. So it's a bit more fast-paced and dynamic here, the scenario. The second point is that existing approaches often build on quite rigid models. For example, for heuristic algorithms or for integer linear programs that are designed by experts and tailored to specific scenarios. And then they work really well in these scenarios, but if the scenarios change and the underlying assumptions no longer hold, then they easily break or at least don't work as well anymore. And then again, we need these experts to sit down, understand the problem, and fix the approaches. And so what we would rather want to have is an approach that self-adapts to new scenarios, to new objectives, and all that without human intervention, without expert knowledge. And then lastly, existing approaches often assume global, up-to-date, or sometimes even a priori knowledge of what's going on in the entire network. And for large networks with monitoring delay, this is not very realistic. And so we really focus here on partial and delayed observations that could be realistically available through monitoring. And we do all of that with a model-free deep reinforcement learning approach. Next, please. Yes, so here's an overview of that approach. On the left side, you see the network, and in that network, every compute node has a scheduling table, and these scheduling tables basically are rules that are applied to incoming flows locally at runtime. And then on the top right corner, you see our RL agent, or reinforcement learning agent, that periodically monitors the network, gets information about what's going on, and then updates these rules inside these scheduling tables, for example, to change load balancing, change the scaling or placement. And this repeats iteratively. And yeah, during training, the agent also receives a reward signal that indicates how happy we are with the current situation, such that it can learn from its actions. Next. So let's have a bit closer look at what these scheduling tables look like. So I mentioned these tables express what to do with incoming flows based on which service a flow requests and which component within that service. So let's assume a flow arrives at ingress node v1, then we see the scheduling table here. And let's assume the flow requests the first component S1, first service S1 and component C1, so the first row in that table. Then with 10% probability, that flow is processed locally at node v1. With 40% probability, it's sent to the neighbor and processed there. And with 50%, it's sent to node v3 and processed there. And that's how we decide the scheduling, or yeah, that's how the scheduling works here. But we also derive the scaling and placement automatically from these scheduling tables in one joint step by placing instances at all compute nodes where flows could possibly arrive. So in order to do this joint scaling, placement, and scheduling with reinforcement learning, we need to define the Markov decision process. And yeah, that's on the next slide, please. So in our case, the Markov decision process is partially observable because we always rely on partial and delayed observations from the last monitoring interval. And these observations contain information about the incoming data rate at the different ingress nodes and about the resource utilization at all the nodes. Then based on these observations, the RL agent takes an action, and this action defines or updates the scheduling probabilities in all the different scheduling tables in the network. So it's quite large and continuous, this action space, which makes things challenging. And then, of course, we still need a reward to give to the agent during training. So we defined our reward function as a weighted sum of multiple objectives. And in our case, we focused on two objectives, on the maximization of successful flows versus dropped flows, and on minimizing end-to-end delay. Next, please. So our again, an overview of our RL framework here. On the left side, again, we see the network that is monitored in step 1, and the monitoring information is processed by an adapter that retrieves the relevant observations, calculates the reward, and passes that to our deep reinforcement learning agent in step 2. And our DRL agent is built on DDPG, so Deep Deterministic Policy Gradient, which supports such large continuous action spaces, and which is an actor critic approach. So in step 3, we retrieve the next action from the actor, again apply that or pass that to the adapter that then applies the new updated schedule and placement to the network. And then this whole cycle repeats, and it repeats a lot of times during training until convergence. So because there are so many iterations during training, we do that upfront offline. And here we focus on exploration to find good actions. And then once the training converges, we switch to online inference. So then we don't need to update our neural network anymore, and it's really fast. And we can do that online. And then we also focus on exploiting the best action rather than on exploration. Next, please. So we evaluated this approach on 4 real-world network topologies, on varying stochastic traffic patterns, and also on real-world traffic traces, and compared it against 3 algorithms. And all the results are in the paper, but here, for time reasons, I just want to show one quite representative result on the next slide, please. Yeah, so here in this plot, you can see on the horizontal axis the number of ingress nodes. So more ingress nodes indicate higher load in the network. And then on the vertical axis, you see the percent of successful flows, where more successful flows are clearly better. And what you can also see is that the blue line representing our DRL approach is significantly better than all of the other algorithms, which is nice. And so based on this result and on the other results in the paper, we can conclude that our approach does self-adapt to varying different traffic loads, different traffic patterns, to different topologies, and all of that without human intervention, without expert knowledge. And it does that very well, so it does process more flows successfully than all of the other algorithms that we looked at. It also generalizes to unseen traffic patterns without any retraining. It supports optimizing multiple different objectives, so also optimizing delay or something in between. Yeah, navigating this trade-off between multiple objectives, and it scales to large networks. Next. Yeah, so this is already my last slide here. Yeah, where I tried to list some of the challenges that we faced yeah, when applying AI for network management. So I listed some of the challenges that I think that we solved here, and also some open challenges at the bottom. Yeah, I'm not sure if I should go through these. I still have 2 minutes, right? Yeah, I'll briefly go through this. Sorry. So when we started this research, we weren't sure how to approach this with AI. So we debated whether to look at typical typical supervised AI approaches, but we saw that there's a lack of data, and typical regression or classification didn't seem right for network management. So we decided to go with RL, and we still had to select a suitable RL approach. And we went for DDPG because of the support for large continuous actions. Then we built a prototype, and it did not work. It did not learn anything. And so we had to debug there a lot. It was quite difficult to understand why it's not working, why it's not learning. And we had to do a lot of iterations here to get it to work. And we had to be very careful in the end also with defining our mark of decision process, particularly with the reward function, to really make sure that this reward function expresses what we want, rather than trying to nudge the RL into doing something and then it learns something different. But overall, I think we solved these challenges, and it works, and the approach does self-adapt to different scenarios. It does scale, it generalizes. So I do think it's an important step towards driverless networks in practice, but I am also aware of the open challenges that are still ahead of us, at least of some here. So I do think we need more standard benchmarks to compare and measure progress in the area. So there are benchmarks in other domains. For example, video games, there's this Atari benchmark. For robotics, there's Muchoko. I think we need something like that. We also need to think about how to bridge the gap from simulation to reality, which is, yeah, non-trivial, I think. And there we need to think about safe and explainable AI, about robustness. And even if we get that all to work on one real network, we still need to make sure that our approach is generalized and can learn online very efficiently if the situations change in these networks. And then ultimately, I think in this approach, we focus on model-free RL, so we don't need expert knowledge, and that's nice. But I think it would also be nice to take and leverage our existing expert knowledge, combine it with AI to get the best results here. And I think here model-free plus model-based could work. So still a lot of open challenges. I think it's very exciting to work in this area, and I'm happy to take your questions. Thanks.
Thank you, Stefan.
There is a question in the chat from Stuart. He was just mentioning causal reasoning. Is it something that's part of, I mean, either your conclusions or future work?
Not yet, no. Is that part of the explainable AI? Yeah, not yet. So I haven't worked or thought into the direction of explainable AI in any details so far, but it sounds very interesting.
Okay, so I mean, Stuart or Joe, you can get in touch if you like, either through the mailing list or directly. I think all the contacts are available. Jérôme, you had a question too?
If you have time for a quick question, maybe. I don't know if it's too long, maybe you can take offline. But a general question, I think thank you, Stefan, and you pointed out one difficult. You have several iterations, in particular regarding the rewriting function. I was wondering if there is any method except try and test in order to see if the rewrite function or try to evaluate if the rewrite function will really measure what you want to achieve. Of course, here you try. I suppose you try, you see the result, and say, "Oh no, it's not maybe the right function." But is there something more, let's say, methodologic to define it? I don't know. Just open question.
That's a very good question. So I think there are a few things or rules to look out for, to make sure to include the relevant metrics, to make sure that the reward is given regularly, so to nudge the RLHN consistently into the right direction. So if the reward is very, very sparse, so only a +1 every 1 million time steps, then it's hard to learn. So the agent needs to get a positive or negative reward or some meaningful reward starting with random action. So if it never gets any relevant reward based on these random actions, then it will never learn anything. So there are a few things to look out for and that I have learned to take into account, but I think there's no cookbook for a great reward function yet. Does that answer your question?
Yeah, perfectly. Thank you.
Yes.
You were in the queue. I think we are really running out of time. So if you have a question to this presentation, please bring it offline or directly with Stefan. Thank you. So we will switch to our last presentation for this meeting, which will be handled by a student of Jérôme. Jérôme, I think you have the slides. Would you like to share now?
I think Matthews will share the screen.
Okay.
So Matthews, if you can request the screen sharing.
Can you hear me?
Yep.
Oh. Oops. Can you see my screen?
Yes. Please.
Right.
You can start, Matthew.
Right. Right. Notes. Okay, great. You can see my screen, right? It's all good. Okay. Hello, everybody. I'm a PhD student at Nmrg and Orange. I work with both labs, and today I'm going to talk about problems and strategies in implementing AI models in network. So with that, so what are some of the benefits of in-network computation? So let's start with like what exactly is in-network computation? It's basically taking an application or a service and offloading parts of it or the whole thing completely on the network, so on the data plane, essentially. There are a couple of benefits that doing this has a lot of benefits. One is the latency reduction. Generally speaking, services are offered by servers that are connected to the network, and having those services in network means that you have a lower response time to requests because they are serviced in the network rather than being routed between different nodes in the network. You have better throughput and congestion control, and this can be because of multiple reasons. One of them is because of aggregation, for example. several systems, for example, machine learning training clusters and stuff, they perform aggregation, and if you can have aggregation performed in network, then of course, because the number of packets going through the network is considerably reduced, you can also it also leads to like an increase in throughput. And finally, you have the power saving benefits. Uh, uh, network well, network devices, specifically switches, are really efficient, and they're designed to do one specific thing, that is to classify and route traffic. So leveraging that capability of a switch to perform computation will save energy, and will also save energy because the end servers can remain idle or go into a low power state, thereby the overall energy savings uh, uh, are considerable. So what are some of the applications that are being pushed in network onto the data plane? There are a lot of security applications like DDoS detection algorithms, anomaly detection classification algorithms that are being pushed. So this could be something like a logistic regression function that runs on a switch and checks flows to see whether they are whether they are anomalous or not. You have low latency applications. This could be DNS caches, uh, uh, which rest completely on the switch, stuff like that. You have scheduling and congestion control algorithms like RCP, which are being completely pushed in which have been there have been various papers related to this. Then you have network aggregation. Uh, Network aggregation use cases where this mostly happens in machine learning clusters and stuff like that, where the aggregation is done in network to kind of speed up the training process. Yeah, and then another common use we see is for device recognition using classification algorithms like k-means, etc., etc. Okay. So, what are some of the what kinds of hardware um, is generally used for in-network computation? So the traditional method is using middle boxes, and you have three types. You have the most basic dedicated custom hardware middle box, which is purpose built to do one specific task, whether it's a firewall or some sort of acceleration, etc., etc. And this is this sort of hardware, you cannot really change it. You cannot really um, uh, do anything else with it. Then you have the more recent and more flexible ones that are coming out, which is with the x86 middle boxes, which is basically a server with a really fast smart NIC. And you have all sorts of stuff like Snort, which is a IDS, network IDS, and the more recent ones like NFV uh, 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 are also becoming more prominent. AWS has a good platform for that. It's called NFV Mano. And then you have the hardware switch-based in-network implementations. This has come because this uh, this kind of came about because of two major things. One, because of a new kind of architecture in SDN called RMT, which is uh, a programmable architecture, and languages like P4, which allows you to describe switch behavior on uh, on switches and smart NICs, etc., etc. So Tofino is one example of such a chip, an RMT chip, which can be which can be controlled by programmatically. So what are some of the drawbacks and limitations? Middle boxes generally tend to increase latency because you have to go through the network stack of these devices. They are generally purpose-built, not flexible, and each new service you want to add, generally speaking, you have to buy the hardware, and this could add to additional costs. And having many middle boxes for various services could easily clog up the network really fast. Programmable switches, on the other hand, switches in general exist in the network, so they're already there, and uh, so that's one of its advantages. But the they're 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 really restrictive devices, so to speak. They don't have much memory on board. Uh, they uh, they don't support many of for AI, especially many of the functions used are real valued functions, and they're not supported natively by any of the programmable RMT or any of the programmable switches out there, any of the models out there. Uh, uh, Most of the logic you can deploy on a switch is relatively simple, so they don't support complex programs, so to speak. They have very basic instruction sets, bitwise operations, basic arithmetic, bit field additions, and stuff like that. They do not have complex instruction sets like middle boxes do. And generally, their pipeline is linear in nature. What that means is that it's forward facing. It generally goes in one direction. You cannot go back a step. It's linear in that way. So many of the algorithms we use for real value computation, etc., they have loops in them, and they have structures like that, and they're harder to implement because of this. And of course, uh, complex feature sets are not available in switches as of right now. So uh, so to counter some of those drawbacks and like limitations of switches, these are some of the current solutions that are out there that have that have been published over the last few years. The most common way to do computation is using lookup tables, and lookup tables are very popular because essentially switches do just that. They look up values, and then they classify packets based on the looked up values. So lookup tables are very popular, and several actually most of the research into computation as such in network is on a switch is using lookup tables. um, so this is one example I've given. You'll see, which was yeah. Then floating point numbers, generally most Python, like they also use floating point numbers, single precision floating point numbers, doubles, stuff like that. Uh, this is considerably hard in a switch because of the way uh, 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 the data types it supports, and uh, the way data is processed. And an alternative could be to use fixed point numbers, which are much easier to handle. Um, some many of the many of the models require complex features, and these features are not easily accessible on a switch. And several papers have addressed this by by using other external servers to embed features in a packet header, and then extract them on the switch for computation. Uh, Another strategy is to break down a task into many subtasks among multiple switches in the network, and then route them through the combined pipeline, so to speak. Uh, uh, and there have also been models where, for example, where you split tasks which a switch can do better on the switch and certain parts of the computation on the CPU. This is one example with it's a system called banana split, which splits a certain part of a binary neural network on a smart NIC, and the other part is done on the CPU of a general purpose computer. So that this some of the work I have been involved with over the last year has been to create pipelines for programmable switches uh, to implement real value functions. So the idea is to take a real value function and then implement a pipeline which will compute that real valued function. Uh, um, so the idea, we want to provide a platform so that we could deploy all sorts of models, machine learning models, and other kinds of models in network. And we wanted a sort of framework that could easily generate that. So how do we do this? We start by, it's the first step, so I'm going to briefly describe how it works. We start by taking a function, and we start by defining these elementary operations like addition, logarithm, division, and we implement them using the mechanisms and the instruction sets that are provided by the switch. That's the first step. Then given a function, so take this f of xy, we break it down into its elementary operations, and we sort of create a graph, a directed acyclic graph, as always. It shows all the dependencies and all the operators and variables that exist. Then we constrain this graph. For example, if x represents a port number, then we know that x can be between 0 and 65,353. If it's x represents bandwidth, then we know the bandwidth of the port, so that could be a constraint. Another constraint here is the sign node over here. We know it will always output something between -1 and 1. So we know the input to log, for example, is always going to be. So we assign constraints to each node, and then we perform aggregation. Since we know that the input to log is always going to be between -1 and 1, in this case, we don't need to store any pre-computation that for any of the other possible values, just for that. So we aggregate, we minimize our graph here, and then we substitute. So back here we have defined a bunch of primitives for each elementary operations. We substitute them here, and we further simplify it. We simplify the graph, and then we use a combination of linear programming to place the various nodes of this computer graph on the switch pipeline. And we also solve something called the rectangle packing problem, which we've mapped to this to reduce error, basically. So in conclusion, in-network computing offers several advantages like increased throughput, latency reduction, power saving, middle boxes, and program switches. The two most common ways of in-network computations achieved. Programmable switches, despite being fast and heavily resource limited, are the most common way of achieving this. Several workarounds have been proposed, as I mentioned before. Currently, given the state of things right now, we are far from having any sort of complex functions. There are several limitations. We can have small functions, but not anything complex or a full network, for example. We have managed to implement logistical regression functions up to 4 variables, k-mean classifications in our lab. And we are planning on expanding it from a single switch into a whole network. So you provide a real value function, and then it kind of splits amongst multiple switches in the network, and then routes traffic based on the computation that needs to be performed. So we are currently working on that. Yeah. Thank you.
Thank you, Matthew. Unfortunately, we are a bit running out of time, and we had no time to take question online. So as for the first talk, I mean, if you have any question, you can just send to the mailing list. And yeah, I'm sorry because we have strict deadline with this time. Sorry. So
thank you.
Yes. So maybe again, I just want to thank you all the presenters, all the participants, and sorry for presenter to be a bit like that, to cut the question time and so on. We'll try to have a meeting a bit less dense for next time. Yes, so thank you again. And so as usual, we will put minutes online. There will be the recording available also on the YouTube channel. And I hope to talk to you soon or see you soon in the close future. So I don't know, Laurent, if you want to say something else.
No, same as usual. Thank you for attending the meeting. We keep in touch, and we will send you information about our next meeting, probably in April.
We can meet in Gather Town now if you want, for people.
Okay. Thanks a lot for the meeting. Goodbye, everyone.
Thank you. Bye-bye.